In this video, we're going to talk about vector and parametric equations of a line in R2. To find the vector and/or parametric equations of a line in R2, we must be given 2 points on the line, or a point on the line and a direction vector. A direction vector is defined to be a vector, m equals ab, that's parallel to or collinear with the line in question. Let's sketch the line that has the point 3, -2 on it with the direction vector m equals 4, -1. Well, we start by identifying the point 3, -2, and you can see we've got it there. And we're going to call that the position vector, because if we can draw that vector first, if we can find that point first, then what we can do is go to the origin and draw a vector out to that point. And that puts us in the position on the line. It literally gives us a position on the line. So if we start at the origin and travel that vector, it puts us on the line, i.e. in a position to then use the direction vector. What we then do, once we're on that line, we're going to then add 4, -1. So we've dealt with the position vector the way we were supposed to, got to the point. Then we're going to go 4 to the right and 1 down, and it'll put us here. And then we'll do it again, 4 to the right and 1 down, and it'll put us in position there. And so we keep on adding 4, -1, and we get more and more points on the line. But we don't just have to go in a positive direction, in other words, add positive multiples of 4, -1. We can also add negative multiples of 4, -1. So instead of going 4 to the right and 1 down, we can go 4 to the left and 1 up, and we keep on doing that. And what we see is that eventually we've gotten all these points by just first getting in position, picking one of the points, getting in position, that's the position vector, and then just drawing multiples of, then just sketching points that are different multiples of 4, -1 away from that position. So now to put it in a summary, to state the equation of this line, we recognize that we started at the origin, then traveled the position vector r0. When we see this written here, I'll refer to that as r0. We travel that position vector, we only do it once, exactly one time. Then we travel any positive or negative multiple of the vector 4, -1 from there, not from the origin. And when we do that, what we've done after the position vector part is we've sketched the line in question. So therefore, to travel from the origin to any point on the line, we need to travel along the following journey. We need to do the r0 position vector exactly one time. And then we need to do that r0 position vector exactly one time. And then we need to do any number of multiples of the position vector m. So we're going to add multiples of the position vector, so we need to have something to call that multiple that is continually changing. Well, what we do is we call that a parameter. So m is the direction vector, and we're going to add different multiples of it. So t can be any real number, like it says here, and we'll just add any real number multiplied by that position vector. So, for example, in this question, our position vector 3, -2, then we added multiples of 4, -1, and basically we added any real number multiple. And so what we have, like we said, is a position vector in the lead, and then we have a direction vector following the t, and the t, obviously we can use any different letter that we want, but that t is called a parameter. So So here it is in red, so this is obviously important. The vector equation of a line in R2 is R equals R naught plus Tm, where T is an element of the reals, where R naught is called the position vector, M is called the direction vector, T is called a parameter. And so in this case, the vector equation of the line is R equals 3, negative 2 plus T times 4, negative 1. T is an element of the reals, where 3, negative 2 is called the position vector, 4, negative 1 is called the direction vector, T is called a parameter, and T will take on every real number possible to then give us an infinitely long line in both directions. Now, if we're given, let's talk about parametric equations of a line. If we're given the vector equation, then to determine the parametric equation is actually really easy. So if we're given the vector equation R equals 3, negative 2 plus T times 4, negative 1, we can actually just think of that as xy equals 3, negative 2 plus T times 4, negative 1. So x is equal to 3 plus T times 4. X equals 3 plus 4T. And then y is equal to negative 2 plus T times negative 1. So y is negative 2 plus T times negative 1, or negative 2 minus T. And again, T is any real number. And those two equations that we just underlined are called parametric equations of the line. So let's do a question together. Determine the vector and parametric equations of a line passing through the points 5, negative 6, and 12, negative 8. Well, the direction vector is the vector containing both of those points. So imagine we drew a graph and we had a line that goes through 5, negative 6, and 12, negative 8. The vector that goes from the point 5, negative 6 to the point 12, negative 8 can be given by an x component of 12 minus 5 and a y component of negative 8 minus negative 6. In other words, our direction vector can be given as 7, negative 2. Now, since 5, negative 6 is a point on the line, then I can say if we begin on the origin and travel the vector 5, negative 6, we will end up at a point on the line. It'll put us in position on the line. So I can call this vector 5, negative 6 the position vector. So I can say that the equation of the line would be R equals position vector 5, negative 6 plus T times 7, negative 2, where T is a parameter, and 7, negative 2, looks like I forgot my arrow there, where 7, negative 2 is the direction vector. And then we can say off of that, once you determine the vector equation, the parametric equation is pretty easy. We can say x will be 5 plus 7 times t, and then y will be negative 6 plus negative 2 times t. Now, you might be saying to yourself, wait a second, how did you know that you were supposed to use 5, negative 6 as your position vector? How do you know you weren't supposed to use 12, negative 8? And the answer is, we could have used 12, negative 8. There's no rule against it. Different people will maybe use different position vectors describing the same line because they're picking a different point as their initial idea of where to get in position on the line. And then you might say, well, okay, that's fine, but what about this 7, negative 2? If I'd have subtracted the other way, if instead of thinking of multiples of 7, negative 2, another person might think of multiples of negative 7, positive 2. And the answer is, that's fine too. Different people can have different direction vectors. Now, everybody's direction vectors, though, will be collinear. If we're doing multiples of 7 to the right and 2 down, then someone else might do multiples of 14 to the right and 4 down, or 7 to the left and 2 up, but everybody will be a multiple of that 7, negative 2. So this, there might be slight variations in this vector equation. Once you establish the vector equation, the parametric equation follows suit automatically. There are different possible correct answers. Now, Given that line that we just discovered, we'll say it was r equals 5 negative 6 plus t times 7 negative 2. Again, forgot that arrow there for some reason. And the parametric equation's given. Let's determine two more points on that line. Okay. So we know already that 5 negative 6 is a point on the line. If we didn't know that, though, we could get it by letting t equal 0. How do we know t can equal 0? Well, t can be any real number. It says so right there. T is an element of the reals. So we can let t equal 0. And if you let t equal 0, x will be 5 plus 7 times 0, which is 5, and y will be negative 6 minus 2 times 0, which is negative 6. And so that would tell us that the point 5 negative 6 is definitely one of the points on the line. Okay. But like we say here, we can let the parameter t have any other real number value besides 0, and we'll get a different point on the curve. So the point you get when you let t equal 0 is valid, but so would other ones be. So let's let t equal 1. Seems pretty reasonable. Well, if we let t equal 1, then we're going to see that x will be 5 plus 7 times 1, which is 12, because x is 5 plus 7t. And y will be negative 6 minus 2 times 1, which is negative 8, because y is negative 6 minus 2t. And so we would get the point 12, negative 8. But if you go back a few slides, it's kind of funny maybe, but if you go back a few slides, you'll see that 12, negative 8 was actually one of the points we were given a long time ago, off of which we built our equation. So let's just assume for a minute they want different points. Well, all we have to do is let t be any other number. So let's let t be negative 1. And if we let t be negative 1, x will be 5 plus 7 times negative 1, or in other words, negative 2. And y will be negative 6 minus 2 times negative 1, or in other words, negative 4. Okay? And you see the math there. And the point negative 2, negative 4 is also on the line. Now you might be wondering, well, can t be an irrational number or a decimal or a fraction or a negative? And the answer is absolutely. T can literally be any real number. And any real number you choose is going to give you a valid point on the line. So let's let t be negative 38. Totally random number. I like the number 38, so let's use it. And if we do that, then x will be 5 plus 7 times negative 38, which is negative 261. Y would be negative 6 minus 2 times negative 38, which is positive 70. And so that's a point on the line. Okay? So those are 2 points on the line, and obviously there are countless others because it's a line. Now, given the line that we just used, again, we'll use the same equation, r equals 5, negative 6 plus t times 7, negative 2, and x equals 5 plus 7t, and y is negative 6 minus 2t. Let's see if those 2 points shown right here, if they're on the line. Okay, well, let's test the point 26, negative 12 in the parametric equations. If we're saying x is 5 plus 7t, then we're saying 26 is 5 plus 7t. And if we're saying y is negative 6 minus 2t, then we're saying negative 12 is negative 6 minus 2t. So if we let 26 equal 5 plus 7t, like we just said, t equals 3. If we let negative 12 equal negative 6 minus 2t, like we just said, then t is positive 3. And since the same parameter value produces an x value of 26 and a y value of negative 12, therefore the point 26, negative 12 is a point on that line. What some other people do instead, and it's equally valid, they might say, okay, I know that 26 equals 5 plus 7t gives me a t value of 3. That part's the same. But then what they do is they'll take that t value of 3 and they'll just directly plug it into the y equation. So they'll say, okay, y is negative 6 minus 2 times 3. Let's see what we get. We get negative 12, and then they'll say, okay, yeah, that's what I was supposed to get. So that in a way, they're using the y to check if it's if that parameter value that gave you the x also gives you the y. If you use that method, it's just as good as the method we used, the other method we used, which is shown in the typed on your screen right there. So both equally good methods. Okay, Now, the other point we wanted to do was negative 23, 3. So again, we're going to let x equal negative 23. So if negative 23 equals 5 plus 7t, we'll do a little grade 9 math. We'll get t equals negative 4. Well, if we let y equal 3, then 3 is negative 6 minus 2t. T is negative 4.5. So that tells us it's close, but it's not actually on the line. And once again, if you're like doing it the other way, that's totally fine. What some people will do is they'll follow the first part. They'll let negative 23 equal 5 plus 7t, which means t is negative 4. And then they'll take that t value of negative 4, they'll test it on the y. So they'll say y is negative 6 minus 2 times negative 4. They'll do some calculations, and they'll come up with y equaling 2. But the problem is y was supposed to equal 3 for that point to be on the line. So in the second way of doing it, we still get that the negative 23, 3 is not on the line, but rather negative 23, 2 is on the line. Okay, now again, let's go back to the exact same line and imagine we've still got this equation. I must have been clicking and pasting a lot because I keep forgetting to put that arrow there. And we've got those parametric equations. What are the x and y intercepts of the line? Well, this is actually a pretty easy process. We know that an x-intercept just means y equals 0. So all we're going to do now, we're just going to let this parametric equation for y, we're going to let it equal 0, solve for t. When negative 6 minus 2t equals 0, that means t is negative 3. So then we're going to take that t value of negative 3 and we're going to plug it in for x, and we're going to find out x is negative 16. So since y is 0 and x is negative 16, the x-intercept is negative 16, comma 0. And the y-intercept, analogous process here, we're just going to let x equal 0. So x equals 0 means 5 plus 7t equals 0. A little grade 9 math on that. You get t is negative 5/7. And then you take that t value of negative 5/7 and you plug it in for that y right there. You get negative 32 over 7, and you've got a y-intercept right there of 0, comma, negative 32 over 7. Okay. And one more time, given that line we just found in the previous example, r equals 5 negative 6 plus t is t times 7 negative 2. Let's see if this is another way we could actually express the exact same line. Maybe it is, maybe it isn't. Well, if this right here, looks like that equation sort of fell over two different lines, so I'll just sort of circle it here. So I get my, seem to have lost my cursor here. Oh, there it is. So we're basically looking at this equation right here. If that can represent the equation of a line, then two things need to be true. First of all, this 19, negative 10 needs to be able to be used as a position vector for the line. That's another way of saying check if 19, negative 10 is a point on the line. If 19, negative 10 is a point on the line, then the vector 19, negative 10 could be used as a position vector. So then the second one is just to say, if that's true, can negative 7/2, comma 1 be used as a direction vector instead of 7, negative 2? And the answer will be yes, if they are collinear. In other words, if they are parallel to each other, because if these two vectors here are parallel to each other, then they're both equally valid direction vectors, because it'll be different multiples to get you to the same point, but you would still be able to go back and forth along the same line so long as those two direction vectors are collinear. So let's do the work now. So is 19, negative 10 a point on the line? Well, the answer is yes. What we do is we let x equal 19, and that means 5 plus 7t equals 19, which means t equals 2. And then at that point, we then let y be negative 10 and solve, and we get t equals 2. So we got the same answer both times. If you don't like doing that, then what you do instead is you take that t value of 2 and you plug it in for the y value. And when you plug that in, -6 minus 2 times 2, you get -10, which is what we were supposed to get if it was a point on the line. So what we've just shown is that 19, -10 is a point on the line, which is another way of saying if we started at the origin and traveled the vector 19, -10, we would get to a point on the line, meaning that would put us in position, meaning the vector 19, -10 is a valid position vector. Okay, part 1 is done. If part 1 fails, then the answer to the question is no. If part 1 failed, then we would say right away, no, that other line cannot represent the same line. But part 1 passed, so now we move to part 2. Is -7/2, 1 a scalar multiple of 7, -2? The answer here is yes. If we take 7 and divide by -7/2, we get -2. Another way of saying that is -7/2 times -2 equals 7. And if we take the y coordinate, that second y coordinate, that second y component, -2, and divide it by 1, we get -2. It's the same number. That's another way of saying 1 times -2 is equal to -2. So if you take both of these statements up at the top and put them together, what we're saying is if you take the vector -7/2, 1, and if you multiply it by that -2, you're going to get the vector 7, -2. Well, that vector 7, -2 is therefore collinear with that vector -7/2, 1, so it's a valid direction vector. So therefore 7, -2 equals -2 times -7/2, 1, so the direction vectors are collinear, so the direction vector is valid. Therefore, since part 1 and part 2 passed, that equation could also represent the same line. Now let's do another one. Finally, we're going to use a different line. Suppose we see the line r equals 5, -9 plus t, 3, -5, and we want a line perpendicular to that, but that also passes through a point -5, -1. Well, since the curve passes through the point -5, -1, we can use the vector -5, -1 as the position vector. Now, the second part, though, talks about perpendicular. So as for perpendicularity, think back to when we discussed perpendicularity in grade 9 math. In grade 9 math, we established that if the slope of a line was a over b, then the slope of a perpendicular line was -b over a or b over -a. Again, so long as we weren't offending any restrictions where a or b was equal to 0. Just for a moment, let's take that out of the possibility. And we said that basically negative reciprocals will give you perpendicular lines. Well, by extension, if you think about it, a direction vector is kind of like a slope, because if we have a, b, and just for a minute, let's imagine a and b are both positive, we're saying travel a units to the right and let's say b units up. That's kind of like giving a slope in a way. And slope is delta y over delta x. And so the change in x and the change in y is very similar to what's going on with the slope. So ultimately what that means is if the direction vector of a line in R2 is a comma b, then the direction vector of a perpendicular line is actually -b comma a, or if you prefer, b comma -a. So all we have to do is take this direction vector of 3, -5, and reverse them, -5, 3, and that would be akin to giving a reciprocal. But if we want to give a negative reciprocal, what we have to do is change the sign on one of those. So we could make it +5, 3, and that would be a direction vector for a perpendicular line. Or if you prefer, once you do that move of switching the x and the y, components and you want to make change the sign of 1, you could have also made it -5, -3 instead. But we'll use 5, 3 as our direction vector of a perpendicular line. So we have our position vector of -5, -1, and we have our direction vector of 5, 3 for the perpendicular line, and that's actually the answer. Technically, there should be a little thing on the end that says t is an element of the reals, reminding us t can be any real number.